Hello, this is Professor Kuehn, and welcome back to Electricity, Magnetism, and Light, a series of lectures at Wisconsin Lutheran College. In our previous readings, we explored what is today called electrostatics and magnetostatics. The former, electrostatics, is a study of stationary electrical charges. The latter, magnetostatics, is a study of static or time-independent magnetic fields. We began in the year about 1600 with the work of William Gilbert and his theory of permanent magnets, and we ended with André-Marie Ampère's study of electromagnetic forces in about the 1820s. Shortly, we're going to step back in time once again to look at the concurrent development of our understanding of light, beginning in the late 1600s with the work of Isaac Newton and Christian Huygens. They had competing theories of light. One was espousing a particle theory of light, that's Isaac Newton, and the other a wave theory of light. We'll continue our exploration of light and end with the experimental work of Young, Arago, and Tyndall in the mid-1800s. After this historical look at electrostatics, magnetostatics, and light as separate and distinct areas of study, we will then see how they fit together, so to speak, into what became known as the electromagnetic theory of light, which was developed primarily by Michael Faraday and James Clerk Maxwell during the second half of the 19th century. Now, before commencing our study of light, however, I'd like to take a short detour for the next 3 chapters or so of this book to look at one of the most significant organizing principles in all of science, what is now called the conservation of energy. It was articulated in its modern form in the mid-1800s by Herman von Helmholtz. He was born in the city of Potsdam in the kingdom of what was then Prussia. Very early, he developed a love of books, especially physics and mathematics books, but for financial reasons, his parents encouraged him to study medicine. In 1837, he obtained a government grant to study at the Royal Friedrich Wilhelm Institute of Medicine and Surgery in Berlin, with the stipulation that he would subsequently have to serve as a doctor in the Prussian army. So after graduating, he was assigned a regiment in Potsdam, where he spent his free time doing experimental research in muscle physiology. At the time, living organisms were thought to possess what was called a vital principle, as it were, which could initiate forces within the organism. How else, after all, could one explain the directed growth and the willful action of plants and animals? After all, when you decide to lift your arm goes up. What's the link between your volition or your will and the physiology of your motion? Helmholtz was uncomfortable with the present philosophy of nature at the time, which seemed to suggest that living bodies were themselves capable of perpetual motion. So, in 1847, informed by his studies of heat produced during muscle action, he published an essay titled On the Conservation of Energy. In this essay, Helmholtz aimed to provide a critical investigation and arrangement of the facts for the benefit of physiologists. The facts to which he was referring were drawn from a wide range of mechanical, thermodynamic, and electrical systems pertaining to the question of whether natural forces are in fact capable of producing perpetual motion. Helmholtz thinks that they were not, and he proceeded to lay out his general theory of the conservation of force, which is today known as the conservation of energy. Consequently, Helmholtz was relieved of his military obligation and was instead appointed a professor at the University of Königsberg in 1849, where he lectured on general pathology and physiology. He would later serve as a professor of anatomy and physiology at the University of Bonn, a professor of physiology at the University of Heidelberg, and a professor of physics at the University of Berlin. While preparing his lectures in Königsberg, Helmholtz conceived of the ophthalmoscope and became the first to obtain a clear image of the human retina. He also measured the rate at which electrical signals travel through nerve fibers, established a number of significant mathematical theorems regarding vortex motion. He wrote a comprehensive treatise on musical theory and the physics of sound perception. That's called On the Sensations of Tone. If you're interested in music theory, you might find that to be a fascinating read. He also carried out investigations of vibrations in electronic circuits, and these electromagnetic vibrations would later be used by Helmholtz's student, Heinrich Hertz, to study high-frequency radio waves, and that would confirm James Clerk Maxwell's electromagnetic theory of light in the late 1800s. What we'll be looking at in the next lecture is the translation, an English translation of Helmholtz's lecture on the conservation of force, which is based on his famous 1847 essay. So we're going to spend some time with this. I'd highly encourage you to read this essay very carefully. There's a wealth of information in here and very insightful writing about many different topics that we're not going to be able to spend a lot of time on everything that he mentioned. So what I'm going to be doing is walking you through this lecture and highlighting what I think are some of the most important features. But once again, I highly encourage you to read through this carefully.